So I thought I'd try a different kind of video today, and we're going to look at some bioactivity data rather than talk about synthetic routes. And all of the psychedelic phenethylamines that Alex Shulgin made are reported in his book PiHKAL, and part 2 of this book is freely available for download from Erowid, so thanks to Erowid for making this resource available for all of us to look at. And this really has a wealth of information about all the compounds that Shulgin made, but it can be a little bit difficult to navigate because you have to go on the basis of the name of the compound. And whilst there is some logic to Shulgin's naming scheme, it can be a bit whimsical at times, and so we have, the 2C series and then the Aleph series and things like Ariadne and Beatrice from the so-called Classic Ladies series. And really, to learn about the bioactivity, you have to go down to the extensions and commentary section, and you can find the effective dose in man after the synthetic section, but it can be a bit difficult to explore the data and extrapolate any trends about the structure-activity relationships. Now, luckily for us, Brian W. Clare has done quite a lot of the boring work of tabulating the activities of these compounds. And so within this paper, there's a table of the activity of all of the psychoactive phenethylamines in mescaline units, so activity compared to mescaline, and this data set can be downloaded from PubChem. So there's this concept in medicinal chemistry called the structure-activity relationship, and this will seem obvious to some of you, but I don't want to assume anything, so we'll go from first principles. And the idea is that this is saying that the bioactivity or the efficacy of a drug is related to the molecular structure, and that makes sense because these molecules are generally binding to some sort of protein receptor which will have a specific shape, and the structure of the molecule determines how it can interact with that receptor. And so by way of example, I've got a few phenethylamines here from PiHKAL, and we've got mescaline, which is the progenitor of all the other psychedelic phenethylamines, and we know the effective dose in man is about 400 milligrams. And one of the first changes that Alex Shulgin made was to introduce a methyl group at this position, making trimethoxyamphetamine. And this has an effective dose in man of about 220 milligrams. So what this is telling us is the activity of the molecule is related to the structure at this position. You add a methyl group, you improve the potency. So one logical question to ask is, if you add one methyl group in this position and gain an increase in potency, can you get even more potency by increasing the size of this alkyl group? And that's one of the first things that Alex Shulgin did. He made this compound alpha-ethyl mescaline, which has another carbon in this position. And there's a whole quite fanciful paragraph in PiHKAL where he's speculating about whether the trend would continue. Do you get a doubling with each additional carbon atom? Do you get a 256-fold more potent compound with an alpha-octyl group? And nowadays this would seem like quite a crazy idea, because we know anything past a propyl or butyl group is not likely to give you any benefit. And Shulgin was a clever guy, so I don't know how much he really believed this trend could continue, but he did actually make the reagents up to the octyl compound, although he never made the finished products, because when alpha-ethyl mescaline turned out to be inactive, he moved on to studying other things. But it's just an interesting look into his thought process and his speculations about what might lead to increase in potency. So, as I've mentioned, AEM turned out to be inactive, and so we know one methyl group here is good, 2 methyl groups, and presumably anything bigger just kills the activity. So that's an important bit of knowledge about the structural requirements. We know the longer compounds are no good. And then finally, this compound came a little bit later again, TMA2, the second trimethoxylated amphetamine. Alex Shulgin found that by moving the methoxy group from this position up here, so we now have a 2,5 disubstitution pattern, the effective dose in man of this compound is about 40 milligrams, so another 5-fold jump in potency from TMA. And indeed, we know the so-called magic of the 2,5 disubstitution pattern. So these are some examples of changes in the structure of a molecule leading to intelligible changes in activity. And so one useful way to think about this is what we would call the SAR landscape. And this is a concept where you consider the idea of a chemical hyperspace, where all of your molecules occupy this many-dimensional space, and you can travel from one molecule to another along a vector, and the vector represents some combination of changes you make to the molecule. And obviously we can't visualize a hyperspace, so we need to collapse it down, in this case, to 3 dimensions. And then we've got these arbitrary coordinates, which means just as we explore around, we're encountering different molecules. And then on the vertical axis here, I've coloured it for potency, and so a more yellow colour and a higher point on the landscape represents a more potent drug. And so you can imagine conceptually, you have a starting point, something like mescaline, down here in this blue valley of low potency, and by making analogues we explore the landscape. And what we're trying to do to improve potency is we're trying to explore the landscape in such a direction that we get up here, like this might be TMA, for example, with a much bigger boost in potency. And so a lot of the phenethylamines in PiHKAL, you can imagine them occupying various points on this SAR landscape, and the goal as a medicinal chemist is to explore this landscape and to find a more potent compound while optimizing the other properties like bioavailability, stability, solubility, and so on. So let's go ahead and start exploring our data set. And so what we've got on this set of axes is every compound reported in PiHKAL and clustered using the UMAP algorithm into this 3-dimensional chemical space. And the UMAP algorithm is driven by some very sophisticated mathematics that I don't understand, but the upshot of it is that chemicals that are molecularly similar in terms of their structure will appear close together in this 3-dimensional chemical space, and so UMAP is a kind of dimensionality reduction and clustering algorithm. And I've coloured the data points by the log of the activity in mescaline units, and this is from the paper that I talked about in the introduction. And so mescaline is here, and if I mouse over it, the structure will appear in the bottom right. And of course mescaline is red with a log activity value of 0 because the log of one mescaline unit is 0. And then everything else, which tends to be more active than mescaline, is coloured on this colour gradient. So a green compound with a log activity value of 1 will be 10 mescaline units, and so on. One thing, of course, that you do miss out on is the qualitative aspect of the activity, right? This is really just a scale of how potent the compound was with respect to mescaline. Okay, so let's start looking at the cluster with mescaline as the parent. So the red point here is mescaline, and we can see the closely related and active near neighbours, the closest one being that orange point, which has activity, and that's trimethoxyamphetamine, which makes perfect sense, right? It's a small change, just adding a methyl group, and we know that increases the activity. There's a yellow data point next door, which is the benzyl oxy version, and we know from plenty of other compounds that generally lipophilicity in the 4 position drives potency. And then we've got a number of other green data points. So what are these? Adding an extra methoxy group. This is 4-methoxyamphetamine here, and this is the point I was making about the qualitative effects. Really, we're just looking at a number here, which is a very reductionist way of considering the potency of these molecules, and I'm sure in the bioassay experiment in man, the qualitative effects of 4-methoxyamphetamine will be quite different to mescaline, but you need less of a dose to induce those effects. And then up here we've got, moving the methoxy groups around and putting a methyl group. And then this light blue compound here is an interesting one, sort of bridging the 2 clusters. And you can see this is a mescaline-like in its substitution pattern, but with a bromine instead of a methoxy group at position 4. And that leads us into the cluster up here at the top. So let's look at the top cluster next, and I'll zoom in a little bit for this one. And so you can tell that this cluster has the most active compounds because we have these dark blue data points corresponding to a log activity of 2 or 100 mescaline units, things that are about 100-fold more potent than mescaline. And what we find in this cluster is some members of the so-called magical half dozen, so things like 2CB and 2CI. We know a halogen at position 4 tended to lead to the most potent compounds. And the really satisfying thing about the UMAP algorithm is what jumps out at us here is some very closely related matched pairs. So this green data point here, 2CI, right next door to the dark blue data point of DOI, and we know that methylation at the alpha position to give the amphetamine gives us a big boost in potency, so 2CI to DOI, and then here we've got 2CB. You can probably guess what this dark blue data point here is. DOB, so again the amphetamine analog of 2CB, so two really nice close matched pairs here. What else do we have? We have 2CC, so that's chloro versus iodo, and we know the smaller halogens tended to be less active. And somewhere around here we should have 2CF. It's a little bit difficult to see the fluoro in the picture in the bottom right, I'm afraid, because of the colouring of the picture. But 2CF is this one, and you can see this is devoid of any activity at all, so we know we need like a big lipophilic halogen here. This is a weirdo compound, 2CSE. As far as I know, it's still the only selenium-containing phenethylamine or even drug that has ever been made. And then just a quick look at some of the other compounds. So down here you can see we're changing the 4-methoxy group to different alkyl oxy substituents, with cyclopropyl mescaline turning up as quite active. In the top right here, these turn out to be sulfur compounds, and if I'll turn on a substructure search here, you can see UMAP has clustered all but one compound that contains sulfur. They all show up here, so really logical clustering on the basis of the structure. And a lot of the active ones here will be in the 2CT series, so you can see 2CT21, 2CT2 with the ethyl-thio group was quite active. Thio analog of mescaline here, and Aleph, so that's one of the amphetamine-based thioethers, so all the sulfur-containing compounds end up here. And then finally in the back corner of this plot we've got these clusters here, and if I mouse over the structures you can see these turn out to be everything with a methylene dioxy ring, and so these really are close analogues of MDMA compared to mescaline. And we've got quite a few active compounds in here as well, so that's MDA, so the sort of des-methyl version of MDMA, and a few other relatives. And then up here this is you could call this a subcluster again, because you can see the methylene dioxy ring has a different disposition compared to the ethylamine side chain. And finally, this is another plot that I made using about 4,000 structures downloaded from PubChem, and all of these compounds have reported activity against the 5-HT2A receptor, and so everything we've looked at today is just in this small cluster which is part of the much larger universe of 5-HT2A ligands. And there's plenty of other interesting chemical matter here which I might save for future videos, but for now, thanks for watching, and I hope you learned something interesting.